If you have two resistors in series and you apply a voltage to them, the resistors will divide that voltage into a fraction of what you started with, and this handy device is called a voltage divider. Let's look at these in a little more detail. Welcome to Scofflow Laboratories. We're going to look at some schematics, interpret some color bands, and do a little math. Here's a few different ways that voltage dividers appear in schematics. They look slightly different, but you'll see they're all really the same. You have two resistors in series. The resistor closest to the voltage in we call R1. The one that goes to ground we call R2. And the voltage out is right in between the two. Now this one looks slightly different, but you'll see R1 is next to the voltage in series with R2, which goes to ground, and the voltage out is right in between the two. Now this one you might recognize as a potentiometer or a variable resistor. One of these. The wiper divides this resistive element into two resistors, but you still have your voltage in. You can fine-tune the voltage out by adjusting the knob that moves this wiper. And then this one goes to ground. This is the equation for a voltage divider, and this is a voltage divider. Here are two resistors in series, and this is two resistors in series, R1 plus R2. We'll find that value and divide it into R2, this resistor, which goes to ground. Then we'll multiply that times the voltage in, which is this yellow jumper right here, to determine the voltage out, which we will compare to a measurement we take right there. First we'll find the values to plug into this formula. So R1 is yellow, violet, brown. 47, brown is times 10, so that's 470 ohms. R2 is green, blue, red. That's 56. Red is times 100, so that's 5600 ohms. The voltage source is a 9-volt battery, and it's a fresh battery, so we'll call it 9.5 volts. We have our three values, and we'll plug them into the equation. R2 divided by R1 plus R2. So let's simplify that. 5,600 divided by 6,070. And we'll simplify that even further. We'll round this off to the first five significant digits, 0.92257, and multiply that times the voltage in, 9.5. And our voltage out is 8.76. Let's take a measurement and see how close we are. .72. We calculated 8.76 and we measured 8.72. What happens if we switch these resistors around? Now R1 is 5600 ohms and R2 is 470 ohms. We'll have a look at the equation. This value will work out the same. The numerator is much smaller, so let's see how that works out. We have 470 divided by 6,070. That rounds off to 0.07742 times 9.5. With this new configuration, the voltage out equals 0.735. Let's take a measurement. .726. We calculated 0.735 and we measured 0.726 volts. What if R1 and R2 are the same, both 5600 ohms? Here's the equation. 5600 divided by 5600 plus 5600. I think you can see where this is going to go. 5600 divided by 11,200 times voltage in. And of course that comes out to 1/2, or 0.5 times 9.5. And when we multiply 0.5 times 9.5, we get the voltage out, 4.75, half the voltage in. Let's verify this with a measurement. There it is, 4.77 volts. We calculated 4.75 and we measured 4.77 volts. That's about half the input voltage. Let's look at the trends in these three combinations. In the first one, R1 was lower than R2. We got 8.72 volts. Then we switched them so R1 was higher than R2. We got 0.726 volts. The voltage went down as R1 went up. And also notice the two measurements we took add up to 9.446, which is just about the voltage in. And over here, when the resistors were the same, we got half the voltage. 4.77 plus 4.77 add up to 9.54, just about the voltage in. And that's how you divide voltage using resistors. And it's not the only way to do it. You can use capacitors and inductors, but that will be a topic for some future videos. But until then, just grab a few parts and try it for yourself, and then come back to Scofflaw Laboratories for some more electronic basics.